Hello everyone and welcome to the YouTube Academic Project series by Spartificial. I am Chinmay Ratnaparke, your host for the video, and today the topic we'll be discussing is something that has puzzled mankind for generations. Now before we begin, if you're new here, hey there, nice to meet you. The video you're watching is one from a special series of videos by Spartificial wherein we bring up such amazing projects to explore and build a base upon problems that might seem difficult, but are just a few concepts away. But it ain't all gonna be boring, okay? Here's something interesting for you. Towards the end of this notebook, you will notice a few tasks, which on completion will yield you a certificate to show off your hard work. Now you can go ahead and put these on LinkedIn or wherever you showcase your professional profile. Let's get started. When we look up into the night sky, each dot up there represents something. It could be a star, a galaxy, or something more intricate, like a quasar. Historically, the existence of the first galaxies was identified in the 17th century by French astronomer Charles Messier, although at the time he did not know what they were. Messier, who was a keen observer of comets, spotted a number of other fuzzy objects in the sky which he knew were not comets. Worried that other comet hunters may be similarly confused, he compiled a list to prevent their misidentification. Messier's list, as it is known, contains information on 110 star clusters and spiral nebulae, which is what they were called at the time. But it is almost 300 years before astronomers figured what exactly these furry spiral nebulae actually were. But it was approximately 300 years before astronomers figured out what actually these fuzzy spiral nebulae were. With the observational capabilities of mankind increasing, it became easier to see more and more of the universe. More observations means more data, which needs sorting and classification. Now, today, as humanity is continuously pushing the realms of possibility with telescopes like the James Webb going out into the cosmos, a model that can classify these objects would automate the entire process. And that is exactly what we plan to do today. So, let's have a look at the workflow that we'll be following today. So, of course, to begin any problem, we first need to understand the dataset. So, we'll be having a look at our dataset here, problem and the dataset. Once we are done with the dataset, we'll need to include our necessary libraries and modules that we'll be requiring to, play around the data. Now that we have imported those necessary libraries and modules, we will be having a look at the dataset and playing around with the data to build it in such a way that our model can understand it. Once we are done with that, we'll be scaling up the data. Now, essentially, this is something that is done to improve the accuracy of the model. And once we are done with it, we'll build the complete model, we'll test it and see how accurate we can get. So let's have a look at our problem and our data set. So today we'll be trying to, predict whether a given dot in the night sky is a star, a galaxy, or a quasar. So before we get to how and from where, let's understand what exactly a star, a galaxy, and a quasar is. A galaxy is a gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter. Now, these are categorized according to their visual morphology as elliptical, spiral, or irregular. One great example is our very own Milky Way galaxy. The image you see here is one captured from Earth. Yes, some places on Earth have so less light pollution that we can see the entire band of the Milky Way with the naked eye. And here's a fun fact. Once, during a 1994 blackout in the United States, Los Angeles residents dialed 911 when they saw the Milky Way for the first time. Now, a star. Everyone knows about stars, right? A star is a type of an astronomical object consisting of a luminous spheroid of plasma held together by its own gravity. The nearest star to the Earth is, of course, the Sun. Now, moving on to the third one, a quasar, also known as a quasi-stellar object, is an extremely luminous active galactic nucleus. The power radiated by quasars is enormous. A typical quasar is 27 trillion times brighter than our sun. And here is something you should know. If you were to place a quasar at the distance of Pluto, it would vaporize all of Earth's oceans to steam in a fifth of a second. Now, let's have a look at our data. The dataset we'll be using for this model is the Sloan Digital Sky Survey DR14. This data contains 10,000 observations of space taken by STSS, where in each observation is described by 17 feature columns and one class column which identifies it either to be a star, a galaxy, or a quasar. The table you are having a look at is basically a combination of two different views: photo object, which contains photometric data, and spectral object, which contains spectral data. Now here we can get away with the first column and the column that names spectral object, because they are just essentially name markers. These are just object identifiers that are given by the STSS to uniquely identify each object. Now, the next two columns that we see here are the RA and DEC, wherein RA stands for right ascension and DEC stands for declination. Now, right ascension, when paired with declination, specify the direction of a point on the celestial sphere in the equatorial coordinate system. These are essentially coordinates for the particular object we are looking at. Now, because this data is collected by CCDs, that is a charged coupled device, which is basically just a light sensitive integrated circuit that captures images by converting photons to electrons, we have the further 5 data columns: U, G, R, I, and Z. These columns are 5 data bands that divide the entire range from the atmospheric ultraviolet cutoff to the sensitivity limit of silicon CCDs, that is from 3000 to 11,000 angstroms. This is in accordance with the Thuan-Gunn astronomical magnitude system. Now, if we move on ahead, we see run, rerun, camcall, and field. Now, these are features which describe a field within an image taken by the STSS. A field is basically just a part of an entire image corresponding to 2048 by 1489 pixels. It's essentially a part of a big image that we are currently focusing at. A field can be identified by run, which is basically the run number, which identifies the number of the specific scan. There is a camera column or a cam call, which is a number between 1 to 6, identifying the scan line within the run. There's a field number, which typically starts at 11 and can be as large as 800 for particularly long runs. This is basically telling us how long for the exposure has been given. And then there is, of course, rerun, which specifies how the image was processed. Now, all of these columns that we currently discussed have been identified from photometric data. Now, if we go ahead to the spectral data, of course, there is the spectral object ID, which is just a name. Then, of course, there is the class column, which is the thing that we'll try to predict here, which is telling us whether the object identified is a star, a galaxy, or a quasar. After this, there are a few physics related variables here. Redshift. In physics, redshift happens when light or other electromagnetic radiation from an object is increased in wavelength or shifted to the red end of the spectrum. Now, coming to plate, each spectroscopic exposure employs a large thin circular metal plate that positions optical fibers via holes drilled at the positions of the images in the telescope's focal plane. These fibers then feed into the spectrographs. Each plate has a unique serial number, which is called plate. This is what the data plate here gives us. Now, the next MJD stands for modified Julian date, which is just an indicator of the date when a piece of STSS data has been taken. Coming to the fiber ID, the STSS spectrograph uses optical fibers to direct the light at the focal plane from individual objects to the slit head. Now, each object is assigned a corresponding fiber ID. This is what fiber ID stands for here. So, this is what is a part of spectral objects, and the remaining ones are a part of photometric data. So now that we have had a clear look at our data, let's move on ahead to importing the necessary libraries and modules for the dataset. We need to import all the necessary libraries and modules, right? So let's have a look at all these modules we are importing. It might look intimidating, but as we go along, you'll know that all of these are just having their basic functionality, and it's not a lot, it's just the essential things that we'll be adding in here. So we'll be importing OS for operating system functionality like we have in Linux. For data handling and linear algebra, of course, there is NumPy and Pandas that we use. For data visualization, we'll use Matplotlib and Seaborn. To manipulate the data and for machine learning based model building, we'll be using TensorFlow, of course, and importing Keras from TensorFlow. To analyze this data, to classify this data, and to work around with this data, we'll be using sklearn. Now, out of this, I have divided it here. You can have a closer look. sklearn model selection and pre-processing is used for the analysis. Classification performance is measured by the metrics, and the regression is done by all of these other models: logistic regression, decision tree classifier, k-neighbors classifier. And then we import warnings so that we don't face anything unwanted as we move along with the process. If you want to read anything more about this, here's a link of all of these right here included in the notebook, so you can have a closer look. Once we have imported the data set, we move on ahead to the exploratory analysis. We just load the data here first by saying pd.read CSV. CSV is the file, this file that is added here. So by importing data, let's have a look at data.head. So we are having a look at 5 columns. This here is giving us a look at the first 5 columns of all of the data of all the classes. So if you have a look, it goes all the way from object ID RADEC to all the 5 bands, to run, read on, camp call, field, to spectral object ID, class, redshift, plate, MJD, and fiber ID. This includes our entire data set. Now to check whether the data displayed is actually correct and is complete, let's check the dimensions of the data. We do this by typing in data.shape. This gives us the dimensions of the data, and as we can clearly see, there are 10,000 rows and 18 columns, meaning 18 different columns having 10,000 data sets each. So as we see that this is correct, we can go on ahead. But as we move ahead, before we send this data to the machine, we need to process it. So why add these unnecessary columns that are just names, right? Spectral object ID and object ID are simply names that tell us which object this particularly is. So we don't particularly need that. So let's remove those data columns. We do this by data.drop. Object ID, spectral object ID. When we type in data.drop and type in the names of the columns and put in the axis as 1, these particular object IDs are dropped. And let's check the next data that we obtain by doing in data.head and writing in 10. We are having a look at 10 rows and all of the remaining columns that we have. So we can clearly see it starts with RA and there is nothing before class and after field. So we have successfully dropped in our 2 different columns that we don't need. So again, to confirm this, let's have a look at data.shape. We get our updated shape as 10,000,16. Yes, 10,000 entries, 2 shapes dropped. To have a nice description of the data, it's always better to do data.describe. This is giving us a description of all our data. So count again 10,000 in each. We have a look at the mean, the standard deviation, the minimum value, 25%, 50%, 75%, and the maximum values, which is a nice thing to have. And all of this we can use visually and mathematically to manually compute if the data set that we are getting from the machine is correct. Once we are done with dropping off these 2 columns, we move on ahead to checking the information about the data. We do this by checking data.info. The reason why we are doing this is so that we can check if there are any null data points included in our data set. as in if there are any entries that do not have any data. We don't need such entries, right? If there are some entries that don't have any data, it means the data set is incomplete. So let's have a look at it. So again, in each of these columns, we have the column names here, and non-null count is 10,000 non-null in each, which is a good thing. And we can have a look at the data type as well. It says float 64, int64, object float64, and int64. Again, if you might know a bit of C++, or if you might know the basics of programming either, so this is what it means. Float64 essentially means data type that contains points and decimal places and values. Integer is pretty self-explanatory. It contains integer points. Object, on the other hand, is our data point that we obtain from the column class. So star, galaxy, these aren't any numbers. These are what come under objects. So there is just one column named object. There are 8 columns under float64, and there are 7 columns under integer 64. So, but we can see that there are 10,000 non-null values in each of these columns. So the data set is complete and there are no voids or missing cells. Since the data set is complete, we move on ahead to classify them. Now, to send this data over for processing, we'll first need to convert all of the data points into numbers. The only problem here is the class, right? Because it is the only one which is non-numeric value. So to convert this, sklearn provides a very efficient tool to encode this. Okay, it's called label encoder. So what label encoder does is it encodes labels with values between 0 and n-1, where n is the number of distinct labels. So let's have a look at an example about it here. When we go down here, we can see, if let's say there is a data set that has person 1 basketball, person 2 football, person 3 basketball, person 5 soccer, and we need to encode this data into numbers. So what label encoder does is it smartly assigns each new entry a number, and every single time an entry is repeated, it uses the same number to reassign it. So if we go down here and see the encoded data, again, soccer is 2, basketball is 0 everywhere, and football is 1. So we'll be using the same thing to encode our data set here. So we'll be using le equal to label encoder.fit. We'll be fitting in this data for the column class. Now, to transform the data, we'll be using this particular line, le.transform. Now this simply transforms the data into the encoded form. Let's have a look at the final data set by printing in data.head 10. Again, this will give us 10 entries and each of the columns. We can see nothing has changed here, but the column class, this has to change. The stars, galaxies, and quasars have now been replaced by 0, 1, and 2. And if we compare, we can have a look that galaxies have been replaced by the number 0, quasars have been replaced by the number 1, and stars by number 2. Let's have a look at the new information of the data. Data.info. Again, there are 10,000 entries from 0 to 9999. There are a total of 16 columns from 0 to 15. These are the column names. There are 10,000 non-null values in each of the columns, and all of the data types are now in int64 or float64. Now we can see that the dataset is complete and has no null values. Since the dataset now has only numerical values, there's no need of further encoding. So we can move on to the training part. So let's split the data into the training and test split that we decided in the very beginning. So as we discussed, there will be a 30-70 splitting between the testing and the training dataset. So let's have X be given as the data by dropping the class data points. Okay, and Y will be the dataset full of class. So now that we have split the data, we need to scale it. Now, what exactly does data scaling mean? Now, this data scaling means converting the data that we have from the entire range of values to a shortened range of values into a percentile kind of value between, let's say, 0 to 1 or -1 to 1, such that the mean value is normally taken to be 0. So you might ask, what exactly is the benefit of data scaling? See, when we have a large amount of data, so let's say spanning between 100 to 900, the model has to individually go from every single data point. 100, let's say the first data point is 100.00001. The model will have to manually go from 100.00001 to whatever the last data point is, 900. It could be 900. So the model will have to individually train itself with such a wide range of data, which will take time and which is not efficient, and which will also reduce the accuracy. To counter this, we do data scaling. Once we scale this data into a standard range, let's say -1 to 1, the gap between the data is reduced drastically, thereby reducing the individual reading time and the processing time. It becomes easier for the machine to learn the data. It becomes much efficient, as well as it is reducing the time by a large scale. So to do this, standard scaler is something that is very useful. So we get this from sklearn.preprocessing. It is a data pre-processing tool. So standard scaler, what it does is it follows standard normal distribution. Basically, it makes the mean 0 and then scales the data to unit variance, which is -1 to 1. And it depends how it chooses the units based on what the amount of data is, or what the distribution of the data is. So once we go down here, from sklearn.preprocessing, import standard scaler. This is basically importing standard scaler here. Once we call standard scaler in, we with mean equal to true, with standard deviation equal to true, we are basically assigning it to have its default values, whatever they are, to process this above data. And now once we fit and transform this data into X, now what was X? X was just our data set which had dropped the class, right? So let's have a look at the scaled and transformed data that we obtained from standard scaler till 20. So if you see, we have it scaled here, right? So you might see here 0000. This is the last sixth entry. To have a look at this, we just go up here. What's the last sixth entry? It's cam call. It says 444444 across everything, at least in the first 10 columns, 10 rows. So once we are down here and we are having a look at this, we can see that it is 0000. So since the data here stays uniform, the standard deviation will be 0, and scaling it will also turn it to 0. So we can see that it has been successfully scaled. We are having a look at the first 20 columns scaled here. So now, since we are already done with the data scaling, let's perform the 30% test and 70% training split here. So we do this by typing in xtrain xtest, ytrain ytest. Now train test split xy with test size equal to 0.3, which is essentially telling the machine that there is a 30% distribution for test, and random state is equal to 128. Now, what exactly is this random state here? If you don't specify the random state, then every time we execute a code, a new random value is generated, and the test and train datasets would have different values each single time. So to avoid this, what we do is we assign a fixed value, like a random state here is 128. So once we assign this fixed value here, then no matter how many times we execute our code, the result would be the same. That is, the same values will be given in the test and train datasets. So this is why we use random state. And once we have the splitting done, we just move on ahead. Well, now that we have done the 30%, 70% split, before we move on to the machine learning models, we should have a look at the data. We should understand the data before moving on ahead with it. So Let's have a look at the density distribution plots of data, as in understand how many stars, quasars, and galaxies are here exactly. So let's have a look at the data class, which tells us the information. Okay, we do this by using SNS count plot. What SNS count plot does is essentially just counts the number of observations of a particular type and creates a bar graph of it. So we can clearly see galaxies are around 5,000, quasars, which is denoted by number 1, are approximately around 1,000, and stars are upwards of 4,000. Now, one thing you might remember is the U, G, R, and I we saw at the beginning in the data, right? U, G, R, I. What were these? These were color bands, where U stands for ultraviolet, G stands for green, R stands for red, and I stands for infrared. Now, to compare all of this data together, we can use a pair plot. Now, a pair plot is typically used to understand the best set of features to explain the relationship between any two variables to see how much they compare and how much they are codependent or independent of each other. So we can clearly see by typing in SNS pair plot data U, G, R, I, and class. You can clearly see how U classifies against G here, U classifies against R, U against I, and U against class. Similar is the case with G, R, I, and class. Now, one good thing here, or one interesting thing here that I'd like to add on is if you have a closer look, you can use this data to see what kind of stars or how many stars, galaxies, and quasars here are a part of the ultraviolet spectrum or the infrared spectrum, and you'll get a more better understanding of how many of them are moving towards Earth and how many of them are moving away from Earth. Because as you move, as two objects, or let's say there's a star that is moving away from Earth on the wavelength spectrum, it will move towards the lower ones, that is the infrared, and the alternative or the opposite ones that are moving towards Earth will appear to have more of ultraviolet data. So yeah, that's how we'll be able to compare these plots. So after this, finally we are here. So um, before we continue, there are three machine learning models that we are going to use here. Now why three? So there are these different models. Each one of them uses a different technique to classify the given information, or rather, we have a data set which needs to be classified. So each one of these will employ a different strategy to classify, and we'll see which one gives us the best accuracy. So coming to the first one, a decision tree classifier. Now, what is exactly a decision tree? It's a tree that goes down and takes decisions so as to split the data into different columns. Now, as the data is being split, it is being classified, and this happens till we reach a terminal point where we can't classify it anymore. So, a decision tree has a basic structure as follows. It has a root node at the top. As we can see here, there's a root node. This is the core question. Then as we move along, there comes decision nodes, which are the things on which decision can be made. And then based on the amount, or the based on a few particular things, the decision is taken, and towards the end we can finally split the data into multiple different places, but these will be called terminal nodes, as in the data cannot be further classified anymore. So decision tree uses a few algorithms like ID3, C4.5, CART, and a lot more. So we'll to understand this, we'll just have a look at the most basic one of these, which is ID3. To understand this, let's go to a example. Let's consider this example here. We can see a decision tree here, which has the main core question as is the person fit? Now the main question where the data is divided into its biggest chunks is age is less than 30. Further, there are two more constraints which say eats junk food and works out. At the end, there is a terminal node which says fit or unfit, and post which there can't be any segregation. So, what exactly is the approach here? A decision tree using ID3 is basically using a top-down greedy approach to build a decision tree. Okay. Now, what is a top-down greedy approach? As in, we start at the top, and when we say greedy approach, we mean at each iteration, we select the best feature at that present moment to create a node. So, by best feature, we mean a feature where the data can be divided into maximum parts. So once we have the data divided into maximum parts, each part individually has less data to deal with, which is good for us because we have to classify data. So ID3 is a top-down greedy approach, which essentially means we'll be choosing the data to create the node at which the best feature is chosen at the present moment. Okay, and ID3 is generally used for classification problems with nominal features only. Just remember this. So again, ID3 uses something called as information gain or just gain to find the best feature. Now, what is information gain? It just calculates the reduction in entropy. We might have heard this in chemistry or physics. Entropy is the randomness of data. Now, it's the measure of disorder. And when we have a lot of disorder in the data set, the entropy is said to be high. So let's say, again, we can see an example here for this. In case of binary classification, where the target column has only two types of classes, entropy is 0 if all values are same, and will be 1 if all values are, if there are equal values on both sides. That is, there is maximum number of distribution. So now to calculate this particular entropy, here is how we calculate it. Now our data set is, considering our data set as S, entropy of S will be calculated as minus of summation of pi into log to the base 2 pi, where I goes from 1 to n. Now here, n is the total number of classes in the target column, p is the probability of class I, or the ratio of number of rows with class I in the target column to the total number of rows in the data set. And moving on to the information gain, which is the main thing that is used here. Information gain calculates the entropy and then uses it ahead into this formula. So information gain of S with respect to a feature column A. Right, now what does this mean, a feature column A? So that particular column that the data is being dealt with. So let's say information gain of this particular column where we can split the data in the data set S is given by entropy minus summation of SV by S into entropy of SV. So to see this in working, you can have a look at this example, which will give you more insight into how this is exactly working. And this has enough calculations and all data given. So I'd suggest you have a look at that example too. For the sake of time, we'll just move in quickly ahead. So this is what a decision tree is, right? It basically classifies the data into as bigger chunks as possible and then moves on with those chunks to classify it further into even smaller chunks. Now, to implement this, we'll be just using DT classifier is equal to decision tree classifier, max leaf nodes 15 and max depth 3, because there are 15 columns that we are dealing with, and maximum depth will be 3 because there are just stars, quasars, and galaxies. This was one classifier. Now there is another classifier wherein we can use linear regression classifier. So typically when we perform machine learning operations, we normally predict a quantitative outcome or a qualitative class. So in linear regression, the input has to be continuous. Okay, it has to be continuous, and the prediction has to be a numerical value. But here we need to predict a qualitative outcome, right? Because we need to predict it into a class. It has to be either be a star, a quasar, or a galaxy. So this task will be considered as a classification problem because we require a qualitative outcome. Now, not all algorithms will fit cleanly into this, and logistic regression is a notable example of this. Okay, so logistic regression is a part of the regression family because it includes predicting outcomes based on quantitative relationships, and unlike linear regression, it accepts both continuous and discrete variables as input, and output is qualitative. So you can see these dots as well as this continuous line will both be accepted, and we can create a prediction of what the next value will be based on that. So when we use logistic regression, we can predict a qualitative output, as in this case, will it be a star, a galaxy, or a quasar? Or we can even predict something like whether a customer will buy this product, a yes or a no. So what this does is it assigns probabilities to the outcomes using a sigmoid function. Now this just converts numerical results into a probability between 0 and 1, and depending on the probability, it classifies into that particular class. So let's say the probability is 0.7. It will approximate it to 1 and will include it in the class where the thing is happening. This is what logistic regression does. To do this, we'll just include LR classifier is equal to logistic regression, open bracket, close bracket. So this is the second type of classifier. And the third one, KNN classifier. Here, KNN stands for K nearest neighbors. Now, if you have seen our previous video on hunting for exoplanets, you might know this is something pretty interesting. What happens in a KNN classifier is it considers a particular number k and it looks for k nearest objects near it. So let's say I have to classify a ball into either footballs or basketballs, and I have a total of 5 footballs near me, and there are 7 basketballs, but they are slightly further away from me than the footballs. In this case, let's say the nearest neighbor I have to see the number k is 3, and in this case what the algorithm will do is it will look for 3 nearest neighbors to it. Now in our case, since the nearest neighbors are footballs, it will assume that the object has to be a football. This is what is happening here. It hinges on the assumption that similar data points are close to each other. This can be good in some cases, and this can be drastically problematic in some other cases. So this is a third type of classifier that we'll be using. Now, this was just a quick intro on the topic. If you would like to know more and see a proper example for KNN that is practical as well, you should go out and check our video on hunting for exoplanets. It is a dedicated video on solving a problem statement using KNN. It will dive deep into the concepts as well as give you a clear step-by-step understanding on how to approach the problem. Please go ahead and watch it. To implement KNN classifier, we'll just use NENE classifier is equal to K neighbors classifier with N neighbors is equal to 3. As in we are setting K equal to 3. Now that we have used all 3 of our models, let's fit the data into the models. Okay, so DT classifier, LR classifier, and NENE classifier. So we'll be fitting in X train and Y train into all 3 of these and then getting the prediction out of these models. So we'll do this by just getting DT classifier.predict X test. And similar for the other 2. Once we are done with the prediction, let's display the results and see for the first 10 predictions that we see. So if we type in ypreds and ytest till 10 for all 3 of these, what we have here is a list of predictions that we can see that we have obtained from the model, as well as a list of what there was in the original data set. So we can easily compare these to see which one is the most accurate. As we can see here, it is 2022002100, 2022002100, 2022002100. All three are same, but don't worry, they are pretty much same just for the last 10. There will be a difference somewhere else. And if we compare this to the original data set, it is again 2022002100, which is pretty good. So, but it is same for all three. Since it is same for all three, we can't really see a deviation anywhere, which is why we need to have a look at the accuracy. Now, before we just have a look at the accuracy that we can see by looking at the prediction and the original set, we need to understand one more important thing, that if we'll have a look at the density distribution plots, there is a huge gap between the number of galaxies, quasars, and stars. We can clearly see the number of quasars is very less as compared to the other two. So there being a huge gap, we can't really have a look at just the prediction and the accuracy. We need to have a look at the classification report. Now, what exactly is a classification report? It is a report that looks something like this. For all three of these, we will have a precision, recall, F1 score, and support. We'll get to this in a little bit. For this is a part of sklearn metrics. So from sklearn metrics, we import classification report. Our target names will be 0, 1, 2, as we can see here. And then we just print it by using decision tree, a classification report for Y preds, Y test, and target names is equal to target names, because target names here are 0, 1, and 2. So we just created a list here and we'll add them here. So once we are done with all three of these, we can have a look at what the classification report says. Now, what exactly is a classification report? So a classification report gives us a better understanding of what exactly is going on in the accuracy metrics. A classification report is based on 4 different categories, which is precision, recall, F1 score, and support. Now, precision here is what percentage of our predictions were correct. As in, it is the ability of a classifier to not label an instance positive that is actually negative. We are actually having a look at the true positives. To calculate the precision, we add in the true positives divided by total sum of true positives as well as false positives. This gives us the precision. The next thing is recall. Recall tells us what percent of positive cases did we catch. So recall is the ability of a classifier to find all positive instances. It can be defined as total number of true positives divided by true positives plus false negatives. So as in true instances. In both cases, the instances were true positives and false negatives. After recall comes the F1 score. Now, what is the F1 score? The F1 score is a weighted harmonic mean of the precision and recall, such that the best score is 1 and the worst is 0. So generally speaking, F1 scores are lower than accuracy as they embed precision and recall into computation. So F1 score is defined as 2 times recall into precision divided by recall plus precision. So for 0, as we can clearly see for decision tree, the precision is 0.99, the recall is 0.99, and F1 score is 0.99 as well. For 1, it is 0.94, 0.98, 0.96, and for 2, it is 111, which is so impressive. We can have a look at all three of these here, and if you notice a common trend, the precision, accuracy, and F1 score in general for 1 is comparatively lower as compared to 0 and 2. This is due to the fact that number of quasars in our data set is very less. So if perhaps we can get more data, which includes more data on quasars, our accuracy will drastically improve and we can get the precision, recall, and F1 score values for 1 as well as other 2 even higher. So if we look at all three of these, since all 3 scores of decision tree are overall better than the other 2, decision tree is the best way to solve this problem. Now, if you have reached till the end, congratulations, you've completed this very well. And now here are a few tasks for you, which on completion and submission, you can perhaps get a certificate. So let's have a look at these tasks. The first one being, you need to try visualizing the decision tree for the above generated model. Now, if you can have a look, this is what a decision tree looks like. You need to create a decision tree of what the above model looks like and submit it here, and you can get certified for solving the problem. Next, you can try correlating these features to come up with a selection that perhaps improves the model performance. Or you can create a function that can predict whether the object is a star, a quasar, or a galaxy by taking in some specific inputs other than the classification column we used here, of course. If you had a closer look at what we went through, you can have a look at these pair plots, and maybe you can find something here to classify it better. So that's pretty much it. And you can submit your solution notebook using this form. You have to open up this form, and once you open this form up, you'll be able to see this is the form. You'll need to input your project ID, the project name, which you'll see at the very beginning of the project. Here, make sure you copy this and paste this well, because if you don't put in the correct project ID, I'm afraid you won't be certified. You'll need to put in the correct project ID and the correct project name. Fill in your other details here. Make sure you put in your email ID carefully too, because certificates will be sent here. Put in your phone number, your everything else, and make sure that you have a profile on Spartificial as well. Okay. Before you submit the solution, make sure you open up spartificial.com and sign up here. Just put in these few details and you can continue with Google as well. Once you've done that, congratulations, you've completed this project. So if you liked the video, make sure to hit the like button. It always motivates us to create more such content. And if you have any doubts or if you have anything to add on, make sure to comment, make sure to share this video. And of course, a subscription always goes a long way. Have a great day. Thank you. The development of technologies to predict and analyze deep space bodies such as stars, quasars, and galaxies has had numerous benefits for humanity. These technologies have allowed us to learn more about the universe and our place within it, which has had a profound impact on our understanding of the world and our place within it. In addition, these technologies have also had practical applications, such as in the fields of navigation and communication. For example, GPS systems rely on precise measurements of positions of celestial bodies to function accurately. Furthermore, the development of these technologies has also created new job opportunities and economic growth as businesses and governments invest in research and development in this field. Overall, the development of technologies to predict and analyze deep space bodies has had a positive impact on society, both intellectually and practically, and will continue to do so in the future.